All right. Hope everybody's doing okay today. We are going to continue graphing the other trig functions. In fact, we will have seen all of them graphically before we leave today. We'll talk about the characteristics, all that good stuff. But before we get to that, the big item, what is happening in 2 days? Okay, you got your exam. Okay, now remember, look for it to have the law of cosines, law of sines on there. You'll want to be familiar with the area of the oblique triangles using, say, the side angle side formula or Heron's formula. Okay, those will probably make an appearance, as well as graphing sine and cosine, all those characteristics. Now, tangent, cotangent, secant, cosecant, those are not going to be on the test. I am going to go ahead and give you an assignment today, which will be due on Friday. That way we get everything wrapped up right before the break. You go to the break not having any homework from me, have a nice restful Thanksgiving. We come back, get ready for inverses and trig identities. All right. But any questions? Remember, what can you use during the test? You got a note card. So we're talking about an index card. It's got to be 3 by 5, not a piece of paper that you tore out that looks 3 by 5 inches. Anything you want to write on here, front or back, is perfectly fine. In fact, I'm encouraging you to go ahead and put the table for the ambiguous case from your law of sines and law of cosines on that card. I have several problems which will be directly tied to the table. Okay, so I definitely encourage you to go ahead and have that. Anything else you want to put on there is completely up to you. All right. So let's see. Yesterday we started talking about cotangent. We reviewed tangent a little bit. So here is the graph of cotangent. Now, tangent and cotangent both have a period of what? It's just pi. So it only takes half as long for their graphs to repeat as it does for the other 4. The other 4 all are going to have a period of 2 pi. That's how many radians is necessary before it cycles again. It repeats itself. Well, what I have read in here is the critical values for cotangent. Okay, they're going to have critical values just like sine, cosine, even tangent did. So this represents one period. So the node solution, the undefined symbol, represents an asymptote. Then as you follow along the y values of these 3 points, see we have 1, 0, -1, and then we finish with another asymptote. Those are going to be real important when we start to graph these. Okay, well, let's just get right into it. See what a transformed cotangent function looks like. Okay, so I'm looking for cotangent of 2x. All right. Now, just like tangent, just like sine and cosine, I'm going to start these problems by creating a compound inequality. Now, if you're trying to graph sine or cosine, you're going to want to put your compound inequality lower boundary 0, upper boundary 2 pi. But for tangent and cotangent, you're going to want to use a consecutive pair of asymptotes. What does consecutive mean? Yeah, one right after the other. So as long as they form a period, you're good to go. I personally always like to go ahead and use 0 and pi. If I'm going to graph tangent, I like to use -pi/2 and pi/2. But really, you can use any pair that you want. Okay, so I'm going to start here. So I'm going to say 0 is less than or equal to pi. So 0 and pi represent my consecutive asymptotes. But I'm trying to graph cotangent of 2x. So what's going to go between those? What's that? Susie? 2x, that is absolutely right. Any horizontal transformations are going to go between your boundaries here. Okay, now typically you'll want to be looking for parentheses. That's a really good indicator of what's going to be horizontal and what's going to be vertical if it's outside the parentheses. Okay, well let's go ahead and solve this. I want to get x in the middle, so what would I do? Yeah, just divide by 2. So I'm going to divide all 3 parts by 2. So 0 over 2 is still 0, 2x over 2 is x, and pi divided by 2. Okay, so this right here is going to help me determine what one period of the new graph is going to be. Okay, and it's also going to help me with x values on my ordered pairs. All right, so we're done with that compound inequality. So I'm going to put him to the side for just a second. Now I'm going to turn my attention to the critical values. These are the y's. Okay, remember these are the ones that I just mentioned a moment ago. The ones in red going from one asymptote to the other. Okay, so I'm going to go ahead and put undefined. We had a 1, 0, a -1, and then we had another undefined, right? Are there any vertical transformations here? Is there any shift, vertical dilation, reflection? Nothing, right? There's nothing besides that 2 inside the function. So those are going to remain exactly as they are. Okay. Now, if I needed to change them, as in the next one, we'll go ahead and do so. But how do I pair up these y values with these x values? What do I do? What do we do with sine and cosine? Yeah, there you go. The lower boundary is always going to go on the first critical value. So I'm going to put 0 right here. The upper boundary is always going to go on the last critical value. Okay. And now here's where we're talking about a particular distance. How far is it from 0 to pi over 2? It's easy, right? It's pi over 2. But whatever the distance is that you have, we always divide by what? Always divide by 4. Will we always do that? Yes. Okay. So what is pi over 2 divided by 4? Pi over 8. So this guy's going to get pretty skinny. Okay. So this value, I took the distance, always divided by 4. So I'm going to be adding pi over 8, starting with my lower boundary. So the first one's easy. 0 plus pi over 8, well, that's just pi over 8. Well, now, what's pi over 8 plus pi over 8? 2 pi over 8, which would be pi over 4. Now, if you want to keep it as the unsimplified version, it may help. What's 2 pi over 8 plus pi over 8? 3 pi over 8. And help me out here. Will 3 pi over 8 plus pi over 8 give me pi over 2? Yeah. Now, should that always happen? Should I always end up exactly at my upper boundary? Yes. Now, if you don't hit that upper boundary, we've made a mistake someplace. Okay. Now, here we go. Now, typically, this is still going to represent one period of my graph, but I've only got 3 ordered pairs here. Why is that? What's happening at 2 places? Yeah. So this point right here that would be considered 0, infinity, no solution, that's just telling me the location of an asymptote. So I'm going to go ahead and put an asymptote at 0, and it looks like my other asymptote is at pi over 2. Now, what's halfway between 0 and pi over 2? Pi over 4, right? So where is pi over 8? There you go. It's halfway between 0 and pi over 4. So here is pi over 4. So pi over 8 would be halfway between that. So I'm going to have to plot a point right there. So let's say that first ordered pair would be pi over 8, comma 1. So I go pi over 8 to the right, 1 up. Then I have pi over 4, 0. And then I have 3 pi over 8s, which would be halfway between the next two, and then -1. So here is my graph. There's one period of cotangent 2x. Where would the next asymptote be? It would just be at pi, another 2 units down. And then I would just copy this same dot pattern again. And there we go. And I can do that as many times as I like. Okay. Pretty sure Mr. Heinrich is going to want at least 2 periods when you do this, for those of you who are moving on to calculus. Okay. But this guy ended up getting real skinny. Is that what we should have expected? Okay. Because what told me that should be happening? Remember, what do we do when we multiply against x? We don't take the opposite. We take the reciprocal. So the reciprocal of 2 is 1/2. So compare this graph to the parent. He is half as wide as he originally was. Okay. If I actually wanted him to double in width or something like that, then I'd start with a fractional factor. Okay. Does anybody have any questions on that? Not too bad. Okay. All right. Well, let's try this next one. You guys are going to walk me through it. I want to graph negative cotangent of pi over 2x plus 1. So we can start with critical values. We can go ahead and start with the compound inequality. What do you like? Okay, Aiden. Okay, compound inequality. Now, since it's cotangent, we're going to choose once again to use 0 and pi. So Aiden, what's got to go between them? Okay. But wait a minute. What about that plus 1? There you go. If you're trying to decide if something is a horizontal or a vertical transformation, well, ask yourself, is it inside parentheses? If I wanted this 1 to be included horizontally, then there should be parentheses there to indicate that. If there are no parentheses like we have here, then that plus 1 has to be a vertical shift. Okay? So I'm going to go ahead and put pi over 2, x right here in the middle. Okay, Miriam, how would I get just a single x in the middle? You want to divide by pi over 2? We can do that. So 0 divided by pi over 2 would be 0. Less than or equal to pi over 2 divided by pi over 2 is just 1x. But now we've got pi divided by pi over 2. What's that going to become? 2. Okay. So I've got my compound inequality simplified. Okay, 0 and 2. Now what? See, these are my x's. We still need the y values. And where do those come from? Okay, remember those are my criticals. Okay, Skylar, what are the critical values for one period of cotangent? Well, he was quick to shake his head no, at least. Okay. Let's see. Who can help him out? Stephanie, can you help him out with that? What were those 5 critical values? For one period. Okay, Satish, you want to help him out? Okay, we start with undefined because we have an asymptote. Positive 1, 0, and then what? Undefined. Those are the 5 critical values, going from one asymptote to the other. Okay. Now, on the previous problem, these didn't change at all. Are they changing here? How do we know? Here we go. There are actually 2 transformations that we need to take care of. So first I need to multiply all 5 of these by a -1. And then I need to do what? Add 1. Yeah, whatever's happening vertically, that's what you're going to apply to your critical values. Horizontally is always going to be in your compound inequality. So what's a no solution times the -1 plus 1? Still no solution. Okay, so that doesn't change. Okay, so that's going to stay the same. Now, let's start with the 1. 1 times -1 plus 1. 0. So all I'm doing is taking the original y values and I'm changing them to what the function wants. Okay? 0 times -1 plus 1. 1. And our last one, -1 times -1 plus 1. 2. So these are the y values I need. So I'm going to erase the originals. And again, if you can do that mentally, perfect. I always like to write them down in case I make a mistake. Now what? How have we gotten the points in the past? Christian?
0 on the undefined.
Okay. He says put the 0 on the undefined. And put the other 2 on the second undefined. Okay. Now how far is it from 0 to 2? 2. But we always do what? Always divide by 4. So a distance of 2 divided by 4 looks like my increments are going to be in 1/2 units. Okay. That's what I'm going to add. Now, starting with 0, I should be able to add that over and over and get to 2. Let's see. 0 plus 1/2, plus 1/2, plus 1/2, and then plus 1/2. Remember, what you end up with, this represents one period of what you're trying to graph, your sketch. So where are my asymptotes? They're at 0 and 2. Those are the undefined. All right, so let me take this out of here. So 0, 2. Okay. Then I have an ordered pair. The first one right here would be 1/2, comma 0. So 1/2, 0. Then I have the next ordered pair at 1, comma 1. And then I have 3/2, comma 2. Okay, so I would say it's going to look something like that. Okay. And at that point, the hard work is done. Now you just have to copy that, probably I'd say one more time. Okay, we're going to shoot for, let's say, 2 periods. So where would the next asymptote be? 4. And I would just copy this point distribution here. So I put 1 right here, halfway, and then halfway. There you go. Okay, that would be negative cotangent of pi over 2x plus 1. That's all there is to it. Is there anybody who's not sure where anything came from, where I got the graph? Okay. All right, well, let's put tangent and cotangent to the side. Now we are on our final 2 graphs, secant and cosecant. All right, well, we are going to go ahead and graph these as well using sine and cosine. Okay, again, referring to them as sinusoidal functions. Now, both cosecant and secant are going to be have periods of 2 pi as well. Remember, the only trig functions that do not have periods of 2 pi are going to be what? Tangent and cotangent. Okay. So the reciprocal of cosecant is what? Sine, right? Okay. So the reciprocal of cosecant is the graph of sine. So we're going to use him to help us out. Now, you remember like we did with tangent and cotangent, we rewrote it in terms of cosine and sine? Well, we're going to do the same thing here. Cosecant is equal to r over y, if you were to evaluate on the unit circle, right? Well, the unit circle, the radius is 1. And what trig function is y? Sine. Okay, so sine is going to be really important to cosecant. In fact, cosecant has a problem whenever sine is what value? 0. See, cosecant can't exist whenever sine is 0. So that's why we're going to go ahead and start with him. In fact, what is sine's critical values? 0. We have a maximum, 0, minimum, 0. Okay, now you want to do this lightly on your paper because you're going to be erasing him. Okay, because our goal is to use him to get cosecant. So here we go. So it's the same idea as when we were looking at cotangent and tangent. Wherever sine touches the x-axis, cosecant will have a what? Okay, so there's going to be an asymptote right here. Negative 2 pi, negative pi, 0, pi, 2 pi. Now, I'm not going to erase sine just yet because he's still going to help me get his graph. Now, we're going to have what we're going to refer to as branches. Okay? Every place that sine has a maximum or a minimum, we're going to have a branch opening away from it. So at a maximum, we're going to have a branch that opens away. Okay? And that's going to occur at every single maximum that sine has. For the minimum, those are going to be opening down. Now, they look like what? They look like parabolas, but they are not parabolas. Not the way we know they're constructed according to their equations. Okay? So we can't call them parabolas. That would actually be incorrect. We'll just refer to them as branches. Now, if I remove sine, what you have left, that is the graph of cosecant. Okay, that's cosecant. Okay, kind of an unusual looking graph. Okay. But just like we did with the previous ones, let's go ahead and tie this back to the unit circle. Okay, let's go ahead and look at these major points here. Let's look at 0, pi over 2, pi, and then I'll even come back and take a look at a few other ones. Okay, so I'm trying to evaluate cosecant on the unit circle. So let's see here. This would be the radius of 1 over y. So let's go ahead and start with cosecant of 0 radians. Okay. Well, at 0 radians, what's the y value? 0. So I'd want to take the radius 1 divided by that 0, but cosecant is undefined. That's why we begin at 0 with an asymptote. Remember, wherever sine is 0, I'm going to have an asymptote. Now, let's rotate pi over 2 radians. Cosecant of pi over 2. So I have the radius of 1. Well, what's the y value at this location? 1. So at pi over 2, we should get 1. Let's go ahead and do one more. From pi over 2, let's rotate to pi. Cosecant of pi. So I'm going to take the radius of 1 divided by What's the y value at pi? 0. So cosecant is not defined at pi. So take a look. We started asymptote, 1, asymptote. So if I go back over here to the graph, at 0, we have an asymptote. Pi over 2 gave me 1. Pi gave me another asymptote. What do you think is going to happen if I rotate to 3 pi over 2? What should I be getting? Here's 3 pi over 2. Should be getting -1, so let's check it. Cosecant. 3 pi over 2. Well, that's still the radius 1 over. We'll rotate all the way around. The y value is -1, so see, I do end up with -1. Hello. Alyssa. Okay. Alyssa. Now, I'm only using some of the major points to go ahead and show you how we're constructing the graph. Any radian measure between 0 and 2 pi is helping to form these graphs. In fact, let's take a look at one specifically. Let's say pi over 4. Cosecant of pi over 4. Okay, so you've got the radius of 1 over. What's the y value at pi over 4 radians? Square root of 2 over 2. And by now, according to the happy minutes, you've done this a lot, right? So if you take the reciprocal, this would be 2 over the square root of 2. And now what would that be if I simplified and rationalized? It's just square root of 2, right? So let's take a look. If I take this information back to my graph, okay, right here at pi over 4, if I were to go straight up to my graph and hit it, and then go straight over, that should correspond to the square root of 2. That should be an additional ordered pair here. So again, you can take as many radian values as you want, continue to plug them into cosecant, and you should form these graphs the further you go. Does that make sense? Okay. Anybody confused by that? Okay. Well, what would you say for his domain? Well, it's definitely all reals except x not equal to, Dylan, what do you say? Pi times, okay, this is the class that likes, yes, that's right. So all of my asymptotes are just multiples of pi, so he's absolutely right. So pi n, where n is an integer. Okay. Now, because we have the excluded values of the domain, which are the asymptotes, we have the asymptotes. They're going to be located at multiples of pi. Okay. But do you notice anything different? Think about the range of sine. What's the range of this guy? Yeah. You notice vertically there's a gap, right? So we go all the way down to negative infinity. We come up, stop at -1, and we are going to include it. Union, and we pick right back up again at 1. So that's the range of cosecant. Okay. All right. Well, let's go ahead and do the same thing for secant. What's the reciprocal of secant? Cosine. So y equals cosine of x. So let's run through the same mentality. Secant of x is equal to the radius over x. But we're on the unit circle, so remember the radius is 1. And what trig function is x? Cosine, that reciprocal, right? So it's the same idea. Again, we're just using cosine now instead of sine. Secant has a big problem whenever cosine is what? 0. So let's go ahead and see where cosine is going to be 0. Let's see. We always start with a maximum. Then a 0, minimum, 0, max. And I'm just going to repeat this curvy V to the other side. And remember, we want to do the graph of cosine very lightly because we're going to be erasing it. Okay, so there's cosine. Here's my even function. Okay, we got that curvy V. Wherever cosine is 0, he touches the x-axis. Secant will have an asymptote. So I have one here, -3 pi over 2, negative pi over 2, pi over 2, 3 pi over 2. But I'm not going to erase him just yet What we just did a moment ago for sines, maximums, and minimums, I'm going to do the same thing here. Wherever cosine has a maximum, I'm going to have that branch that opens away from it. But it's going to be bound between these two asymptotes that we have. Okay. Wherever it has a minimum, those are going to be opening down. Okay. And now I'm going to erase cosine. And there we go. There is secant. Okay. All right. And you'll notice, again, I said the period of these two was going to be 2 pi. It takes a branch both opening up and down to create one period. In fact, basically what we've got for each of these is showing 2 periods on a graph. Okay, so it contains a branch opening up and down. All right. So what are the locations of all those asymptotes? What would we say? Let's see, who haven't I talked to today? Fawaz, help me out here. What are the locations of all those asymptotes for secant? A little off, because see, an integer can be 0, so pi over 2 times 0 would give me 0. But we don't have an asymptote at 0. No. Now, we are going to use pi over 2 as a starting point, but think of it like this. If I'm at pi over 2, how many radians does it take to get to the next asymptote? Pi. And the next one. There you go. So he says x cannot equal pi over 2 plus pi times n, where n is an integer. Okay. That also gives me the asymptotes because that's the excluded values of the domain. So x equals pi over 2 plus pi n is an integer. And do you notice anything about the range? Yeah, it's the exact same as the range of cosecant. Negative infinity to negative 1, union 1 to infinity, and we're going to include those. Okay. So these are the graphs of cosecant and secant. And again, these are what you're going to come to know as cofunctions as well. Because these are side by side, you're going to be able to see this a lot easier. If I take the graph of cosecant and I phase shift it pi over 2 units right, what's going to happen? Okay. Will I get the other graph? Yeah. Okay, they were called cofunctions, just like sine and cosine are cofunctions. Tangent and cotangent are going to be cofunctions. Someone just know? Okay. Hello. All right, we are to our last problem today. I'm pretty sad about it too. All right, I want to graph 2 cosecant of 1/2 x. Now, it is true. You can go ahead and take secant, cosecant, run through the transformations, get the sketch, just like we've always done. Well, just like I could show you. But I think there's an easier and a faster way where we actually don't even have to learn any new material. What's the reciprocal of cosecant? It's sine, right? So the reciprocal of this function, 2 cosecant of 1/2 x, would just be 2 sine of 1/2 x. You remember a second ago how I used the graph of sine to get cosecant? I could use this graph to get the graph of what I want. Okay. Negative 2 secant of 3x. What's the reciprocal of secant? Cosine. So I would say negative 2 cosine of 3x. And see, the really nice part about this, do we already know how to graph sine and cosine? Yeah, so that is no new material at all, but we can use those to get these graphs that we want. Okay, so let me show you. I want to graph 2 sine of x over 2 because that's the reciprocal. All you have to change is just the trig function itself. Everything else remains the same. Now, because we're going back to sine and cosine, what are my boundaries for the compound inequality? What do we do on the homework? Really?
You mean the lower boundary?
Yeah, for your compound inequality. For
For
sine and cosine.
sine and cosine, it's 0 and 2 pi.
0 and 2 pi. That's absolutely right. So 0 less than or equal to 2 pi. Now, if we were actually going to go ahead and try to graph this using cosecant, we'd have to go ahead and use asymptotes on there. But we couldn't use consecutive because it takes more than consecutive to get a period here, which makes it a little more difficult. All right? But we're going to go back to sine. What am I going to put between 0 and 2 pi? X over 2. Whatever's inside the parentheses, I'm going to put inside. Okay. Now, how would I simplify this? Which will give me what?
X.
Less than or equal to x, because the 2's cancel. Less than or equal to 4 pi. Okay. Got him taken care of. He's good to go. Okay. Now, let's turn our attention to the critical values. What were the critical values for sine? Remember, he started with a 0. Okay, maximum, minimum, and then back to a 0, right? Are there any transformations here that I'm going to apply to these? Okay, just the 2. The only transformation I see that is not in those parentheses is the 2. Now, what am I going to do? Am I going to add, subtract, multiply? What do I do? Yeah, whatever you see it doing in the function is what you're going to do to these values. So 2 times 0 would just be 0. Okay, 2 times 1 and 2 times negative 1. Okay. There you go. Now let's go ahead and pair the x's up with the y's. Okay. So Xavier, how do I do that?
You're going to use your lower and upper boundary.
Okay. So what should the first ordered pair be?
0.
Okay. So 0, 0. 4 pi goes with the last one. And again, this is an easy distance to work with. Okay. We take that distance and we always divide by 4. So what am I going to be adding? Just one what? 1 pi. There you go. So 0 plus pi is pi, plus pi, plus pi. And then plus pi does get me back to 4 pi. Okay. So now let's plot my points. We have the coordinate 0, 0. We have the coordinate pi, 2. So I go pi to the right, 2 up. Then I have 2 pi, 0. Then I have 3 pi, negative 2. And finally, 4 pi, 0. Okay. And just like I've always done, we can repeat that pattern, bless you, going in the other direction. So this will be right here, 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 and here. Now remember, I'm going to go ahead and draw him very light. Now this is the graph of 2 sine of 1/2 x. But that's not what I want. I want 2 cosecant of 1/2 x. So what have we talked about today that actually gives me the graph now? Satish, what do you think? Yeah, everywhere this graph touches the x-axis, 2 cosecant of 1/2 x is going to have an asymptote. There we go. And what else? The maximums and minimums that we have will be those branches that look like parabolas. So I'm going to have one here, I'm going to have one here, opening down, just like this. And now I'm going to erase 2 sine of 1/2 x. And what's going to be left, there's the graph of 2 cosecant of 1/2 x. Okay. That's what we're going to be doing. So you can probably already see, how we're going to graph the next one. Right? Questions. Is anybody having trouble with that? Anybody not sure where something came from? All right. Let me go ahead and give you your assignment. Is there anybody else out there who needed the key? Anybody who needed the key and did not get it? Okay, remember, when's this due? It's due on Friday. Okay, We still want to practice this, but we want to go ahead and make sure to get it done before the break. Okay. Or, I don't know, a week is a long time to go without math. Maybe you do want something to do over the holiday. I can respect that because math is super fun. I can see it by the look on all your faces. Hey, last ones. Now, I want to go ahead and point this out to you real fast. If you start looking, numbers 5 through 16 are just sketching these graphs. But on different problems, like number 5, it asks for C over B, 2 pi over B. And then 6, it says left and right asymptotes. I'm not interested in those. I'm just interested in you being able to sketch these graphs. Okay, so I'm not concerned with that. I'm just going to be looking for the sketches. Okay, come Friday.
You don't have to do the period thing, stuff like that.
I'm not worried about that because in doing it this way, you're going to find the period anyway. Okay, you're going to have everything you need. I'm not worried about that. 5 through 16, only thing I'm going to be looking for are the sketches. Now, if you want to go ahead and do that to give yourself more practice, by all means, please. But I'm not concerned. Okay, so that is all we got for today. Connor, if you will turn on your light. And we still have about 4 minutes, I'd say. Oh, my goodness.